In this video, we are going to discuss on very simple and basic concept, that is acidity and basicity. Very often, you can find one question based on this particular topic. Generally, they give a few compounds and they ask to predict the increasing or decreasing order of their basicity or acidity. First, let us see what is meant by acid. Acid is nothing but proton donor. According to Brown's concept, acid dissociates in solution to give H+. But when we go for organic chemistry, we go for acidic proton. This acid term can be used only for carboxylic acid and sulfonic acid. But the acidic proton refers to the proton that can be abstracted by a base. So acid and acidic, they are not same. For example, if you go for acetic acid, this proton will be released in water. So it is acid. When I go for nitromethane, if I dissolve in solution, this H+ will not be released. Even in solution, it will remain as CH3NO2. But if I add a base, then this hydrogen will be taken to give carbanion and H2O. So this proton is acidic and this is acid proton. Second one, base. Bases are compounds that accept proton or that can abstract the proton. Generally, when you go for base, it will be anionic species like C-, N-, O-, or it may be compound with lone pair of electron. It may be on nitrogen or oxygen, even sulfur. But sulfur is less common. Generally, we come across nitrogen and oxygen. In this video, we are going to discuss the acidity and basicity on three topics. The first one, factors that affects acidity and basicity. This is very important. Very often, question is asked based on this topic. The second one, how do we express the acidity and basicity? It is nothing but Pka value and Pkb values. Even though you can use pH to express the acid and base strength, this pH can be used only for acid and base, not for acidic proton. Because of that, pH is not commonly used in organic chemistry. We go for Pka, which can be used for acid as well as acidic proton and bases. So Pka is more general compared to pH. And we are going to discuss about the acidity of conjugate acids. First, let us go to the factors that affect the acidity and basicity. First, let us discuss on the factors that affect the acidity and basicity of organic compounds. I have given some of the factors which can affect the acidity. The first and most important one is electronic effect. It may be resonance, inductive effect, or even no bond resonance. I have also included electronegativity under this category. The second one, hybridization. The hybridization of the atoms. It may be sp, sp2, or even sp3. That may affect the acidity as well as basicity. The third one is aromatic character. Aromatic compounds are more stable than non-aromatic and anti-aromatic. So the compound will prefer to become aromatic if there is any possibility to become. Thereby the proton will become more acidic or less acidic also. The fourth one, it is solvent. Based on dielectric constant, the acidity and basicity will change. Next one, size of atoms. If the size of atom is big, then the affinity between the proton and atom will be less. Because of that, it will become more acidic. In addition to that, we have also ring size and bulkiness of the molecule. So they also can contribute to the acidity as well as basicity. First, let us go for electronic effect. The first and simplest one is inductive effect. Mainly, it is because of electronegativity of atoms. The electron density is pulled towards atom which has more electronegativity. For example, I go for a carboxylic acid. Let's go for acetic acid. When this bond moves towards oxygen, what we get is proton. If the bond goes over oxygen easily, in that case H plus will be released easily. That will be more acidic. Here I have CH3. Suppose if I go for CF3, since fluorine is more electronegative compared to hydrogen or carbon, the electron from carbon will be pulled towards fluorine atom. Because of that, I will get some del plus here. So the electron from this carbon will go towards this. Similarly, from oxygen it will go towards this. Since the oxygen is going towards this side, this H plus will be easily released. Because of that, trifluoroacetic acid is stronger acid compared to acetic acid. Already I mentioned, inductive effect is mainly because of electronegativity. You may know fluorine is more electronegative compared to chlorine. That is more electronegative compared to bromine. Iodine has the least electronegativity in halogens. So if I go for trifluoroacetic acid, that will be stronger acid compared to trichloroacetic acid. That will be stronger than tribromoacetic acid. That will be stronger than triiodoacetic acid. Even I can go for 1 fluorine atom, 2 fluorine atom, 3 fluorine atom also. When I go for trifluoroacetic acid, this will be stronger acid compared to difluoroacetic acid. This will be stronger than fluoroacetic acid. Further, this will be stronger than acetic acid. I can also compare like this. More the number of electron withdrawing atom, more will be the acidity. I can also go for a compound like this. Compared to benzoic acid, 2-fluorobenzoic acid is stronger acid. The reason, Since it is more electronegative, it will pull the electron. As a result, the H plus is readily given. Suppose if I go for 3-fluorobenzoic acid. Here also I have fluorine atom, but the position is on third carbon. The distance between the fluorine atom, that is more electronegative atom, and the high oxygen is increasing. When the distance increases, the effect will be less. It cannot pull the electron from oxygen that much easily compared to this. Because of that, the acidity of this will be somewhat lesser than 2-fluorobenzoic acid. At the same time, it will be higher than benzoic acid. When it is on the third carbon, still there will be some inductive effect. The magnitude will be lesser than 2-fluorobenzoic acid. I can go for chloroform, dichloromethane, and chloromethane also. Here I have 3 chlorine atoms. They are more electronegative compared to carbon. Because of that, there will be del plus. This proton will be more acidic. In the case of dichloromethane, I have only 2 chlorine atoms. Because of that, the acidity will be somewhat lesser compared to this. So chloroform has more acidic proton compared to dichloromethane. This has more acidic proton compared to chloromethane. Here, if you use sodium hydroxide, you can abstract this proton. In this case, you need stronger base like methyl lithium. I go for phenol and 4-nitrophenol. Here, the lone pair involves in resonance. Because of that, this becomes more del plus. It can be taken by base like sodium hydroxide and it is more acidic. When I add NO2, the NO2 group, since it is electron withdrawing group, it will pull the electron cloud from oxygen. As a result, the del plus on this hydrogen will be more compared to phenol. Because of that, 4-nitrophenol is more acidic compared to this. Similarly, if you go for trinitrophenol, this will be more acidic compared to this. Because here I have 3 nitro groups, all are electron withdrawing, they will pull the electron density from oxygen. Because of that, this hydrogen may be released easily. This compound is known as picric acid. Even though there is no carboxylic acid group, we refer as picric acid because this proton is readily given in solution, similar to acid. I can explain the effect of resonance effect in imidazole and pyrazole. The first one, imidazole, this is pyrazole. This lone pair of electron involves in resonance to give aromatic property. I have another nitrogen which has lone pair. In this, it is observed that this nitrogen is more basic compared to this. The reason is this lone pair of electron will go like this. As a result, the electron density on nitrogen is increased. When there is more electron density, it can readily take the proton, so it is more basic. Similarly, you check what is DBU, diaza bicyclovundecane. A similar explanation can be given for the higher basicity of DBU. Also we have DBN, but DBU is most common base we use in laboratory. The third point in resonance is the alpha hydrogen of ketone, aldehyde, nitro compounds and nitriles. This particular proton is more acidic. The reason, when the proton is taken, the resulting carbanion will involve in resonance. As a result, we get enolate. A similar observation can be given for nitro, nitrile, aldehyde, ester also. The alpha hydrogen will be acidic, that can be taken by base. The resulting carbanion is resonance stabilized. The second concept is hybridization. I go for compound with sp3 hybridization, sp2 hybridization and sp hybridization. Sp hybridized is stronger, is more acidic compared to sp2, that is more acidic compared to sp3. What is the reason? When it is sp hybridized, the S character is 50%, P character is 50%. When it is sp2 hybridized, 33% S character, 66% P character. When it is sp3 hybridized, 25% S character, 75% P character. Now, when the S character is more, the S orbital will be very close to the nucleus. The attraction will be more between the nucleus and the electron. So the bond pair electron is very close to the nucleus, so it is attracted towards nucleus. Because of that, the bond goes towards the carbon nucleus. This hydrogen is free, so it can be abstracted by a base. That's why hydrogen that is attached with sp carbon is more acidic. It can also affect the basicity. For example, I go for pyridine and piperidine. I have nitrogen lone pair, here also lone pair of electron. In this, piperidine is more basic compared to pyridine. What is the reason? Here the nitrogen atom is sp2 hybridized, here is sp3 hybridized. The S character for this is 33, here only 25. Since it is sp2 hybridized, this lone pair of electron is very close to the nucleus, but here it is not that much close to the nitrogen nucleus. The attractive force between the nitrogen atom and the lone pair is more. Because of that, it is not readily available to attack H+. But here it is somewhat more available. Because of that, it can abstract the proton easily. As a result, it is more basic compared to pyridine. So the hybridization can affect the basicity as well as acidity. The next point is aromaticity. Consider these two compounds. When I abstract this proton, what I get is cyclopentadienyl anion. This particular species is aromatic. Cyclopentadiene is non-aromatic. When I abstract the proton, it becomes aromatic. So this particular reaction is more favored. The non-aromatic compound tries to become aromatic by losing its hydrogen. So it will readily lose the hydrogen to achieve the aromatic property. So as a result, this will be more acidic. In this case, when I abstract the proton, what I get is anti-aromatic compound. This one, it is non-aromatic. Anti-aromatic compounds are less stable compared to non-aromatic. Because of that, this particular reaction is not preferred. So this hydrogen cannot be easily removed. This can be easily removed. This cannot be removed easily. Even though both are similar. The hydrogens are attached with two double bonds. Here also same. But because of aromatic property, this hydrogen is less acidic. It can also affect the basicity. This particular nitrogen, even though it has lone pair, it cannot act as base. If I add H plus, it has to become like this. This particular compound is aromatic. You have to consider the lone pair of electron on nitrogen also. This one, it is non-aromatic. So aromatic compound will not prefer to become non-aromatic. So this reaction will not take place. The nitrogen lone pair will not take H plus to become this one, because during that reaction the aromatic character is lost. Because of that, the basicity of this nitrogen decreases. On the other hand, if I go for pyrrolidine, it will readily take H plus to give pyrrolidinium salt. Because this is non-aromatic, this is also non-aromatic, there is no effect of aromatic property. The next one is solvent. When we discuss about solvent, you should know the dielectric constant of solvent. For water, the dielectric constant is very high. Second one, DMSO. Third one, acetonitrile. After that, we come across alcohol. Then chlorinated solvent like chloroform, DCM. When the dielectric constant is more, the acidity will be more. For example, take acetic acid and dissolve in these solvents. The acidity will be more in water compared to acetonitrile, alcohol and other solvents. When you go for solvent, you should remember the dielectric constant of most common organic solvents. If you know that, then only you can predict. So the acidity and the dielectric constant, they are directly proportional. Higher the dielectric constant, higher will be the acidity in that particular solvent. Next one, size of atoms. To explain that, I go for HF, HCl, HBr, HI. HI is stronger acid compared to HF. The reason, the size of iodine is very big compared to size of hydrogen atom. The nucleus is in the middle. Because of that, the attractive force between hydrogen and the iodine nucleus is very less. So this hydrogen can be easily released. On the other hand, when you go for HF, both are small. The two nucleus, they are very close. The attractive force will be more. So when the size of anion is big, the acidity will be very high. HI is stronger acid compared to HF. Next one is ring size. To explain this, I go for cyclopentadiene and cyclohexadiene. Because of keto group, the alpha hydrogen is acidic. Which one will be more acidic? It is observed that 5-membered ring proton is more acidic compared to 6-member. When this proton is taken, the ring strain is released to some extent. Because of that, it is more acidic compared to 6-membered ring. Similarly, when I go for pyrrolidine and piperidine, pyrrolidine is more basic compared to piperidine. So the ring size can affect the acidity and basicity to some extent. The last point is bulkiness. Already we have discussed triethylamine is less basic compared to diethylamine. Electron density on nitrogen is more. Because of bulkiness, it cannot take the proton easily. That's why secondary amine is stronger base compared to tertiary. When I discuss about acidity and basicity, I have to discuss also about Pka and Pkb values. Very often they ask to arrange the compounds in the increasing or decreasing order of their Pka value or Pkb values. It is very easy if you know the acidity and basicity. In addition to that, you have to remember that acidity and Pka values are inversely proportional. Higher the Pka value, lower will be the acidity. Similarly, basicity and Pkb values are inversely proportional. Another interesting thing is acidity and basicity are inversely proportional. So if you know this, it will be very easy to arrange the compounds in the increasing order of their Pka values. It is not compulsory that you should know the values, the Pka values for a particular compound. If you know the increasing order of the acidity, that is equal to decreasing order of Pka. This particular topic will not be complete if I don't discuss about conjugate acid-base pair. Now to explain this, I go for ammonia and water. To this, I add some acid. Say I add HCl. Similarly, here also I add HCl. You may know this is base, this is acid. When they react, what we get is NH4 plus Cl minus. Similarly, here H3O plus Cl minus. Since it carries minus charge, this is base. This can donate proton, so it is acid. Similarly, this is base, this is acid. Now the base becomes acid, acid becomes base. Now these two are known as conjugate acid-base pair. Similarly, these two are conjugate acid-base pair. You may know ammonia is stronger base compared to H2O. You may also know that H3O plus is stronger acid compared to ammonium plus. So if you compare the conjugate acid of stronger base is weak acid. Conjugate acid of stronger base is weak acid. Conjugate acid of weak base is stronger acid. So this is conjugate acid-base concept. You may be given a few protonated species. You may be asked to arrange them in the increasing order or decreasing order of their acidity. For that, you have to go for the parent compound and you have to compare the basicity. Based on the above discussion, I have some practice problem. Try to solve these problems. First one, arrange the following in the increasing order of their basicity. They are given pyridine, piperidine, pyrrolidine and pyrrole. Which one will be more basic and what will be the increasing order? Here you have to use the concept of aromaticity for pyrrole. Between these two, you have to use ring size. Here you have to use hybridization. Based on this, you have to arrange these compounds in the increasing order of their basicity. This also is a similar problem. Arrange the following in the increasing order of their pKa. They are given 3 compounds. The first 2 compounds are fluorobenzene, but the hydrogens are different. Here the hydrogen is next to fluorine, but here it is in the para position. The third one, it is phenylacetylene. Which one will have higher pKa value and which one will have lower pKa value? You should know acidity and pKa values are inversely proportional. Here you have to use hybridization concept. In this too, you have to use inductive effect. Arrange the following in the increasing order of basicity. They are given 3 compounds: pyrrole, imidazole, pyrazole. Here you have to use the concept of aromaticity for pyrrole. In imidazole, you have to use resonance. Based on that, you can predict the order. Next one, arrange the following in the increasing order of their acidity. I have given 3 compounds. I have marked the hydrogens also. The first and third are active methylene compounds. The second one is not active methylene compound. Here you have to use the concept of resonance. Also, you should know NO2 is stronger electron withdrawing group compared to aldehyde. Then next, ketone. After that we have ester. Finally, amide. This is the order of electron withdrawing capacity. In this problem, I have given 3 benzoic acids. You have to arrange the following in the increasing order of their pKa value. First one, 4-trifluoromethyl benzoic acid. Second one, 2-trifluoromethyl benzoic acid. Third one, 3-trifluoromethyl benzoic acid. Here you have to use the inductive effect. Resonance is not possible here. You have to go for inductive effect. CF3, it is electron withdrawing group because of more electronegative fluorine atom. Among the following, the more acidic proton is. I have given 4 compounds. All have active methylene protons. In that, which one will be more acidic? When you compare the first 2, you have to go for the concept of ring size. When you compare second and fourth, you have to use the concept ketone is stronger electron withdrawing group than ester. This is the next problem. Arrange the following in the increasing order of their basicity. Which one will be more basic? When you go for compound A, there will be resonance of the lone pair. When you go for compound B, there will be bulkiness. It is tertiary amine. Compound C is very well known. It is known as DAPCO, diazobicyclooctane. Here the amine is tertiary amine. At the same time, since it is locked, the steric hindrance will be less here. So that you have to consider. This is the next problem. Find out the correct statement about triethylamine and quinacridine. Quinacridine basically bicyclic compound. Triethylamine is more basic than quinacridine. Triethylamine is tertiary amine. Quinacridine also tertiary amine. But there will be bulkiness here. It will not be in quinacridine since it is locked. Quinacridine is more basic than triethylamine. Triethylamine, quinacridine have same basicity since both are tertiary amine. Last one, triethylamine is less basic due to steric hindrance. You have to find out the correct statement or statements. In this problem, I have given two compounds. Each compound has two nitrogens. So totally there are 4 nitrogens. In that, which one will be more basic? The first one is known as DBU, diazobicyclooctane. The second one is similar compound, but there is no double bond. I have marked the nitrogens as A, B, C and D. Which two will be more basic? Here you have to use resonance. On this will involve in resonance. As a result, the electron density on this nitrogen will be huge. Here you have to use the concept of bulkiness. Tertiary amine is less basic compared to secondary amine. This problem is based on conjugate acid. Here I have given 3 compounds. All are protonated species. Arrange the following in the increasing order of the pKa. I have highlighted the nitrogens also. Which one will have higher acidity or which one will have higher pKa? Remember, acidity and pKa, they are inversely proportional. When you go for this, you have to use the concept of aromaticity. In this case, you have to use resonance. Using that, you can predict the answer. The last problem, it is based on the acidity of acid in different solvent. When you dissolve acetic acid in different solvent, what will be the acidity? I have taken 4 different solvents: water, DMSO, methanol and diethyl ether, in which the acidity will be the highest and in which solvent the acidity will be the least. You have to find out that. This problem is based on the dielectric constant of solvent. If you know the dielectric constant, you can solve this problem very easily.